Okay, so the discussion today is going to be around this idea of the side splitter theorem, and it really it predicates on the concepts that we've been learning so far. So if I look at this, there's the ratio way of doing things, and then there's this idea that if lines are parallel, then I'm able to really generate a lot of really good information about the similarity or the dilation that could have occurred. And so as you're looking at this picture, we can see a little bit of information, but when they're talking the ratio method, essentially what they're saying is where you use the ruler and you multiplied by the scale factor. And then the parallel method is where I have a ratio. I multiply one side and then I construct the parallel line. So I start here, and this would be like step one, and then step two would be making this parallel. And what this does is it maintains ratio, and the ultimate result is that the ratio ends up being the same down here as it does up here, and I can have R times OB is equal to OC. Okay, some other results from this is the corresponding angles are equal, and we can get similar triangles by angle, angle, angle. And we'll cut that down to just angle, angle. And so using this, we come up with a theorem, and that's ultimately what I wanted to focus on today. So this says the fact that the ratio and parallel methods are equivalent is often stated in what we call the side splitter theorem. To understand the side splitter theorem, we need a definition. And so right here is the definition. Side splitter, a segment CD, is said to split the sides of the triangle OAB proportionally if C is a point on OA, D is a point on OB, and then the ratio is equal. And so we would call CD a line splitter. And so sometimes I've seen this as part to whole equals part to whole, or you can always reverse these. Whole to part equals whole to part. It's ultimately what's important is that your ratios are equal. So we're going to highlight that. Okay. Now the actual theorem is a line segment splits two sides of a triangle proportionately if and only if it's parallel to the third side. So we've seen this if and only if before, and what it really does is allows us to view the wording both ways. And so the restatement of that is if a line segment splits two sides of a triangle proportionally, then the segment is parallel to the third. The other one is if a line segment is parallel, so we're starting off with parallel, to a side of a triangle, then it splits the other two sides of the triangle proportionally. And you can see the diagram here. Essentially, it ties back to this highlighted part. And so they're looking at the part of the segment versus the whole segment. With part of the segment to the whole segment. And so when you set up the ratios, they have to be equal. And so I wanted to make sure that we've seen this. The lesson summary is up above. Triangle side splitter theorem. A line segment splits two sides of a triangle proportionally if and only if it's parallel to the third side. You're going to see several problems that look like this. And how it works is, say I took my ruler and I measured these out, and I see that this is approximately 3.1, this is 5.2. And this is approximately 3.7, and that one was approximately 6.1. And if I take these ratios, so if I look at 3.1 divided by 5.2 versus 3.7 divided by 6.1, so there, a calculator, and we'll do 3.1 divided by 5 2/10. You get approximately 5.962. And then I look at the other ratio, 3.7 divided by 6.1. We get approximately 0.607. So there could be a little human error in here, but what they're trying to state is that since these two proportions, let's just say I rounded them, and it's 6/10 and 6/10. Since these two things are the same, that implies we have parallel lines. And so AB is parallel to A prime, B prime. Okay. The last part here, they give us the fact that we have parallel lines. So XY is parallel to AC. So important that this is not drawn to scale. We can sort of use this idea to solve a question. So OA over OA and OB prime over OB. Keeping that formula in mind, what I can do is I can look at OA. Well, that's really, and you get to choose, but let's just say that that is BX over BA. Does that equal BY over BC? And we know it should be because of the parallel lines piece. So this tells us that they should be in proportion. And so this equation just sets us up to be able to solve. So BX is 4, BA is 5, BY is 6, and they want us to figure out that value. And so a little cross multiplication, or really the way I like to look at it is if I multiply both sides by X and both sides by 5, These simplify to a 1. These simplify to a 1. So I get 4x equals 30, and x is equal to 7.5. So my result is BC equals 7.5 units. You can set this all back up again. BX over BA is equal to BY over BC. And since BX is 9, BA is 15, this equals BY, which is 15 over BC. Just another way, instead of using the variable, I can just use the letters as is. And again, I could multiply both sides by BC. That makes a 1. Multiply both sides by 15. And so I get 9. BC is equal to 225. And BC is then equal to 25. And so you can use this to solve problems because we know since parallel lines implies proportionality, and proportionality implies parallel lines. These are direct result of the two types of techniques we've sort of been covering, or we'll talk about. One being this ratio method, where you essentially took your ruler, measured out, or you used your compass, measured out. And the other one is parallel lines, create those similar triangles, and then we know things are in proportion from there. Okay, so I'll leave you with the side splitter theorem if you didn't have time to write it down. Thank you for your time.